Let's talk a little bit about reflections. This will also be important for when we start looking at standing waves. Reflections basically occur anytime you have an abrupt change in the medium. And I'll show you this with the wave demonstration device here, okay? But we can imagine there's two changes we could have in a medium, right? We could have a fixed end, right? This is fixed, like this is attached to the wall. And the interesting thing about fixed end reflections is that if you send an up pulse, a down pulse will come back. Okay, they actually invert. And then we could also have a free end, okay? And a free end, if you send an up pulse down, you'll actually get a reflection that is the same orientation. You'll get an up pulse back. So these will have an upright reflection. This will have an inverted. Now understand also, it doesn't have to be totally fixed. Let's imagine that we go from something that's fast to something that's slower, harder to move, right? You'll get an inverted reflection. And if you go from something that's slow to something that's fast, then you'll get an upright reflection. And this is a fundamental principle of waves. Okay. Examples here. This is light reflecting off of the windows at a particular angle. Light reflecting off the water. Light actually slows down quite a bit when it hits the water, so that's an abrupt change. It can go through the water, obviously, right? But it reflects off the water. This is light reflecting. That's not very nice. Light reflecting off of a metal coating on the bottom of a sheet of glass. That's a mirror, right? Okay. This is partial reflection, so sometimes not everything is reflected, right? And then, of course, this is what photographers like to do. There's lots of pictures of light reflecting off of lakes before the wind has disturbed the surface. More examples of this. Sound can reflect. There's a place in Wisconsin where we stand across a lake and you can shout and you can hear your reflection off the end of that lake. And of course we would do this. We kind of creep ourselves out because it would sound like another person over there, right? This is a church that's got some incredible reverb time. Look at all these curved concrete surfaces. This is, for some music, this is great, not so great for things like jazz, right? This is the St. Paul Cathedral. I've actually performed in this cathedral, and it was interesting because the tempo affected the sound of the music, and that's because the reverberations meant that when you were singing, you were also harmonizing with something that you had just sung, which I thought was cool. This is Notre Dame. And our family actually saw this in 2004. Incredible acoustics, but they had signs all over saying, "Don't sing." I wanted to sing in Notre Dame, but they wouldn't let you. So I respected that. More examples of this. Anthropologists were actually confused and they couldn't understand how Polynesians could, in the South Pacific, how they could navigate. They could go 100 miles, hundreds of miles between islands, which you can only see about 30 miles of islands, right? And then it's like you can't see them anymore, right? But they could go hundreds of miles between islands, and they could navigate as if they could see the islands. Finally, the anthropologist, asked them what's going on. They could see the reflections of waves off islands that were over the horizon. Now, the anthropologists couldn't see it until they actually sat and took the time to learn how to read the waves. But the native Polynesians could do this too, that's kind of cool. How about a long distance telephone call? You call your sister in France, right? And there's your phone system, then it transfers to a cable or satellite, then it transfers to the French phone system. Each of these boundaries could have a reflection if it's not handled properly. And so you go, hi, how, R, you, and then you hang up and you hope to get a better connection the next time you call, right? There are two ways you can prevent reflection. The first is that you just, don't make there be no change in medium. So you run US copper all the way over to the phone on the other side of the Atlantic. This is not practical, right? You can also just make the change less abrupt. You can make it more gradual. Let me give you, I've got a demonstration of this. But one example of this is if, say, you have an 8 ohm stereo, 4 ohm speaker, the problem with this is that you'll get reflections off the speaker, right? But you can get an impedance transformer that makes it gradually go from 8 ohms to 4 ohms, and then you don't get those reflections. You get better sound. You won't get the distortion of the reflections. Another example, right? I've got a demonstration of it. You can coat telescope lenses so that the light slows down. And there's actually kind of you can make it like wavelength specific, which is kind of cool. And then, an acoustic impedance transformer. Let me just show you this. This is an acoustic impedance transformer, right? This is the bell on a horn. Now, if you took this bell off, the horn, no sound would basically get out of this horn. It would all reflect inside the horn. Another example of making sound so it doesn't reflect is to make the change very gradual. So this is like baffles, and the sound will not reflect off these walls, which is they use this for recording. They'll use this for sort of moderating the echoes in a room. And truly anechoic rooms they'll use for sound studies, right? What's interesting is when you tour these rooms, right? The voice of the tour guide, if they turn away from you, you suddenly can't hear them. You sort of hear this muffled sound, right? Because the sound normally, if somebody looks away from you, the sound will reflect off the walls and you can hear it. But in these chambers, it won't reflect, so you just don't hear them. It's the weirdest thing. Okay, and then we already talked about how the fixed ends will invert it, the free ends will send it back upright. And we will do this. We'll do a lab about this, right? And then another thing that's kind of cool, and we're not going to really get into optics, but the angle of incidence, and physicists measure the angle right there. The angle of incidence equals the angle of reflection. So if it's a plane mirror, you'll get this beautiful reflected light ray like that. And here's another example of this, right, showing the wave fronts. If you have a rough surface, you still have angle of incidence is angle of reflection, but it's since the surface is rough, they come off roughly like that. So this is like you're looking at a piece of paper or something. Anyway, that's all I really need to say. We've got a lab that we'll do for this.